Good afternoon, everybody. If you're listening, my name is Scott Hamill. I apologize that I can't use my video. The connection is slow where I am, so wanted to make sure that you could hear me okay. I'm from the Civil Engineering Department here at UAA, and I'm here to introduce you to today's speaker, Dr. John Thornley. Actually, first time I've gotten to say that. John recently finished his PhD with the University of Strathclyde in Glasgow, but most of us know him as a longtime geotechnical engineer and seismic expert here in Anchorage, working for Golder. So with that, I will, and we'd like to thank John for giving our seminar this week. With that, I will turn it over to John and he can give us his presentation.
All right, great. Thanks, Scott. Appreciate the opportunity to be here today and with you virtually. I'll go ahead and get started here. And so the title of the presentation today is Location, Location, Location. And really what that, if you've heard some of my previous presentations, especially about the November 2018 earthquake, talk a little bit about how it changes, or the way you feel the earthquake or the shaking, how much it changes across Anchorage. And that was primarily the focus of my research while studying at the University of Strathclyde, was how that variability affects Anchorage, and then also, what we should expect in the future. And so this presentation is aimed at sharing a few of those lessons learned from this research. So with that, we'll get started. I should, starting off, I need to thank Drs. Utpal Dutta and Joey Yang of University of Alaska Anchorage. They've been tremendous help in the research that we'll be presenting here, and my advisor at Strathclyde, John Douglas. So thanks to those folks. A little bit about what we're going to talk here about. We're going to talk about South Central Alaska earthquakes and some nonlinear soil response, and how that will affect what we see in our results. Talk a little bit about the strong motion stations we have in Anchorage, and then site response observations, some building code impacts, and then we're going to focus a little bit on what we call response spectrum. We'll talk about that. And then the next big earthquake, and what we should anticipate as the engineering community from that. So with that, I'll just throw up. This is a plot of earthquakes, or more significant earthquakes that we felt in Anchorage between 2004 and 2019. And what we can see here, I'll turn on my laser pointer here. All right, so what we can see here is we've got Anchorage, and what these lines are contour lines. Is you have the subducting Pacific plate subducting below the North American plate, and so that's that interface of the two plates. And so you can see that it's diving pretty steeply as you go to the west there, and so it's fairly shallow, and then it dives more deeply west of Anchorage. We've also got superficial faults, crustal faults, like the Castle Mountain Fault, and then we have some faults within the Cook Inlet that are also shown here. These dots are the epicentral locations of the earthquakes between 2004 and 2019 that are magnitude 4.5 or larger. Generally, in the engineering realm, we don't spend too much time looking at the smaller earthquakes because they don't cause the damage the bigger earthquakes do. So we've got this magnitude 7.1 Anchorage earthquake from 2018, the Inniskin earthquake from 2016, and then the big one, the 1964 Great Alaska earthquake, magnitude 9.2. This is the epicentral location. However, the rupture plane was much more significant than this, and it ruptured quite a bit south of this spot. So So don't want to sell it short here. So just talking about the earthquakes that have been fairly significant. The November 30th, 2018 Anchorage earthquake. We've got the Alaska Earthquake Center's diagram here showing where the earthquake occurred. It was within the Pacific plate. So we've got the North American plate over top of the Pacific plate here, and this is this cut section through the ground that's showing this this diagram. And so you can see that this main shock occurred within the Pacific plate. And it was roughly 47 kilometers deep. But notably, it was the largest event to really impact Anchorage since the 1964 earthquake. And the duration was roughly 20 to 25 seconds. And we had a number of failures and issues that we've talked about before. So just to put it in perspective, we had the 1964 Great Alaska Earthquake, where the duration of shaking was roughly 3 to 4 minutes. And so it's been, as if you took the time from when I started talking till now, we would have been feeling strong shaking. So it's a fairly significant and substantial earthquake. However, one of the things that we didn't have that we do now is strong motion stations nearby. And so the Sitka and Fairbanks both had strong motion stations, but we didn't have anything closer than Fairbanks. And so we're in a lot better place now to record earthquakes. And just to give you a sense for what we have in Anchorage, we have more than 35 strong motion stations located around town, and they're fairly well dispersed around town. And so each of these are the stations. We also have 6 instrumented buildings, including the Atwood building downtown, the VA hospital in northeast Anchorage, and a few others. The Benson building, which was the BP building, and a few others. We have a couple of bridges that are also instrumented, and then we also have this Delaney Park downhole array that has sensors down to about 200 feet or 60 meters below ground. And we'll talk about that here. We also have a varied geologic environment, and this is the primary reason for this varied response across Anchorage. So we have the Chugach Mountains, where we have rock up near the surface, and then we have this Chugach Mountains dips fairly deeply and quickly, and then we have glacial till and a few other soil deposits over top of the bedrock. But the bedrock is quite deep as you move to the west. And so you can see here we've got a variety of units, but we have a number of stations all located within these different units, and gives us a sense for what we can feel across Anchorage. Now, I want to note this K216 site. This is a site located on rock, and we'll kind of talk about this site, and we're going to compare everything that we see here to this site a number of times, just showing what the increase in shaking compared to the rock site is. And so we'll touch on that a little bit, but just want to bring that to your attention while we have this graphic up. So talking a little bit about that earthquake database, you can see that the database of earthquakes that we used from 2004 to 2019 was primarily in the 4.5 to 5.5 magnitude. And so we got a lot of little earthquakes, but only a handful of earthquakes larger than 5.5. So and so we've got epicentral distance from Anchorage here, and this is our magnitude 7.1 event in 2018. This is the magnitude 7.1 event in 2016, the Inniskin earthquake. And so these are our two notable 7.1s that we have, and you can see how great a distance they cover. We also have these broken down by crustal earthquakes, intraslab and interface earthquakes. And so the interface are the earthquakes that are happening actually on the interface of the subducting plate. So with that, we talk about small earthquakes and big earthquakes, and oftentimes, because you don't get that many large earthquakes, seismologists like to use the smaller earthquakes to understand the signature of those of how the soil and rock behaves in a region. However, engineers are a little more interested in big earthquakes, and we want to see what happens as the ground shakes when we have large earthquakes. And so oftentimes engineers say, if we go back to this slide, they say, well, you have all these little earthquakes, but at the end of the day, who cares, because there was no damage there. And what can you tell us? And that's been a challenge over the years, is collecting a lot of little earthquakes. How do you utilize those little earthquakes to understand what behavior will be like with large earthquakes? And we're actually going to talk about that a little bit later today, as we developed a tool to help with that, bridging the gap between those two issues, small earthquakes and large earthquakes. How do we use those small ones to guess and understand what large earthquakes will do? So first we'll talk a little bit about soil non-linearity, so I'll use steel. So steel here, we have a stress strain diagram, and once you take once you load up this steel with stress, to some point you break out of that elastic stage, and ultimately, as long as you stay on this stress path, you maintain, you don't have any permanent deformation. But once you extend past that, then you have permanent deformation. And so in building design, bridge design, and that, we primarily design for the behavior within the elastic range, so things don't move. Soil, however, is not as forgiving, and it has a significant non-linearity. And so even with a little bit of loading, there's the potential that you'll have permanent strain or permanent deformation in it, which can show itself as settlement. It can show as movement, and as what we would just call failure. And so soil is pretty tricky. It's terrible in tension. You can pull those soil particles apart. It's much better in compression, but it does have that nonlinear behavior. And so with big earthquakes, we end up exciting the soil and finding its nonlinear behavior, which is why the earthquake engineers are looking more at the large earthquakes, whereas with the small earthquakes, we stay down in the lower stress, and so the permanent deformation is pretty insignificant. So how do we get that shaking, and how does that affect us? Let's talk a little bit about shear waves. So shear waves, or S waves. If you have that slinky, if you have a slinky and you have a friend holding it at one end and you're holding it at the other, and you shake it back and forth, your slinky will shake back and forth like this diagram here, and you'll see this shaking back and forth. Now, if you push the slinky towards your friend, you get the compression waves, or P waves. And so there are two different types of waves. There are other waves as well, but we'll focus primarily on the shear waves. But the shear waves are those waves that shake back and forth. And so why do we care about those? In soil, shear waves are the waves that cause a lot of the damage that we see in earthquakes, especially at earthquakes that are a little farther away. So these vertically propagating shear waves, these shear waves shake through the soil column, and they shake your building back and forth. And buildings are much more sensitive to shaking back and forth than they are that P wave or that push, because a lot of our infrastructure is built for vertical loads. rather than lateral loads. And so lateral loads end up being the weak spot. So you have these vertically propagating shear waves that impose this lateral loading and shake your infrastructure. Shear wave velocity is also a fundamental characteristic that we can use to understand the behavior of different materials, including soil and rock. And so shear wave velocity ends up being this fundamental piece where the stiffer the material is, the higher the shear wave velocity is. The softer the material is, the lower the shear wave velocity is. And so we can measure the shear wave velocity to understand what what the behavior of a material will be like soil and rock. And so how do we do that? We can do shear wave velocity measurements in situ, so down the hole, case hole suspension logging, cone penetration testing, cross hole. These are all methods of downhole. And then surface MASW and SASW, multi-channel analysis of surface waves, is a pretty common way to not have to stick a hole in the ground to measure shear wave velocity. And so this is just an example of the shear wave velocity profile at Delaney Park downtown. So in Anchorage downtown, there's engine 556, and just to the west of engine 556 down there on E Street and 9th is our downhole array, and we have sensors at the surface, and they go all the way down to 60 meters or 200 feet. And they tag this glacial till that's a fairly dense material, which ends up classifying itself as engineering bedrock. So the engineering bedrock is just a really stiff material. And then you can see as we get into the bootlegger cove formation that clay formation, or the formation with some clay in it, we find much lower shear wave velocities, and then we get into the alluvium, sands and gravels over the top, and our shear wave velocity picks up again. Anyway, just as an example of what that looks like. And so you can come up with an average shear wave velocity for your site, and in the building code, we see that the shear wave velocity we take the average of the upper 30 meters or 100 feet to estimate what the site response will be. And so just kind of talking about that a little bit, VS30 is how we address shear wave velocity within the building code. And so in the 2018 building code, we actually have 5 different site classes, A being very, very stiff or high shear wave velocity, down to very soft sites with low shear wave velocity. But what we're going to see in the next building cycle is a further division of the shear wave velocity for sites. And again, this is that estimate of the upper 100 feet or 30 meters of shear wave velocity, but you can see that we've broken this down to a BC, and then we have a C that kind of fits within the C here, and then an overlapping CD and D. Anyway, the reason I bring this up is because I'll show you a shear wave velocity chart of what we've estimated for Anchorage, and this is using a number of stations, our strong motion stations, and estimating the shear wave velocity based on the waveforms that we've recorded, the earthquakes that we've recorded at these stations. And then we have a number of sites that have actually measured shear wave velocity within them. So this gives you a sense on this side of the of Anchorage, the east side. We can see that we've got much stiffer soils, and then of course rock. And then as we move into the central portion, it gets softer, and then much softer to the west, and then it picks up again on the far west. And so we also have these kind of deeper areas, and these deeper areas actually match very nicely with the deeper portions of the Bootlegger Cove formation, where we have 50 to 60 meters of Bootlegger Cove materials in these spots, and it shallows up in between them. So get a nice match there. So this contour map is based on a whole bunch of measurements. However, as I note here, there's some geology that would definitely help sharpen these lines or divide these lines a little bit better than what we have now. So this is a work in progress, if you will, but it does give you a sense for the shear wave velocity variation across Anchorage. So moving into, how do we understand how site response will be at a site, and how will a building behave at a selected site? We can perform site response analyses. And so for simple structures, we can use the code and understand or utilize our site class shear wave velocity estimate to just use the code and run it that way. Then more complex structures, we can actually do ground response analysis. And this is typically done for taller buildings, dams, large storage tanks, and the like, and more important structures, if you will. Then very complex structures, we get into much more complex modeling, such as, say, nuclear power plants. So we're going to primarily focus today on the more complex structures and kind of the tools that we use to address that. So estimating site response, it's essentially the current gold standard is to run, to capture and measure shear wave velocity at your site. The upper 100 feet is what's used in the building code. However, as I mentioned before, we have 200 or plus feet in some instances of softer materials. And so if you were to work at a site with a fairly deep soil deposit, you'd want to be able to capture those deeper changes in shear wave velocity. So this kind of, with the building code, it assumes that you have engineering bedrock within 100 feet, and that's maybe not always the case, which would then suggest that you should go out and do further studies and then model that for your site. So examples of site response analysis is you can use fairly simplified tools to look at the equivalent linear, what we call the equivalent linear modeling, where we make some estimates about how that non-linearity changes using simplified techniques. And then we also have tools that we can use to understand non-linear response directly. And so we'll focus today primarily on the simplified models. And then we'll also look at, but we won't dive into this too deeply because there's a lot of other fun things to talk about. So for site, Delaney Park, the downhole array here, like I said, we've got strong motion sensors down to 200 feet or so, 61 meters down into the till. And this gives you a sense. So what we can do at this site that's pretty neat is we can actually take a ground motion from the bottom, and then we can see how it propagates and how it changes its signature as it goes to the surface. And this is a whole another presentation all to itself. But this is a great opportunity to really understand how things shake. And so we can calibrate a model. We can take a model and develop that model and calibrate it to understand how this soil changes the earthquake ground motion as it goes through it, and with a shear wave velocity profile and some modeling, we can predict the next big we can predict the behavior at the surface for the next big earthquake. So just talking a little bit about that, we recently did measure the shear wave velocity at the site down to 60 meters, 200 feet. And we developed a model based on what we measured, and we published it back in 2018, right before the November 30th earthquake. So we had this model that we developed, but we didn't really have any kind of big earthquakes to test out the model. And so again, just showing the shear wave velocity profile, we have kind of these stiffer alluvial soils over top of the Bootlegger Cove materials, and then the glacial till of this engineering bedrock. And so if we put a ground motion in our engineering bedrock in the model and propagate it through, we can estimate what it looks like at the top. And so just a little side note, these equivalent linear models don't do very well with big shaking. And so if you went down the path of doing site response analysis in Anchorage for bigger earthquakes, these equivalent linear models wouldn't likely work out. But the November 2018 earthquake was not big enough to break the model yet. So we were able to test our model based on that earthquake. And I've shown this site or this plot before, but this is the response spectrum. So this is a single degree of freedom oscillator. If you had this 1 degree of freedom oscillator shaking back and forth, with a little bit of damping, 5% in this case, these would be your over different periods of shaking. This would be your acceleration. And so this is a response spectrum, and what it essentially means is if you had this building, let's say roughly 10 stories, would have a rough period of about 1 second. You end up with about 0.35 Gs of shaking in that building for that. Now, if you had a really short structure, say a 2-story house, your shaking is much higher, about roughly say 0.7 G. So for this earthquake ground motion, we have significantly more energy in the lower periods, and then it dives off towards the longer periods. Now what we have is the measured earthquake response spectra. If we just looked at the top here, so this was the measured spectrum, and then the model that I had mentioned is here in orange, and it's actually a fairly decent match to what was actually measured. So we took the ground motion that was measured in the bottom, and we went through our model, and we got the roughly the same answer with respect to that. So that tells us that our model did a good job at predicting behavior. And so we've used that as a tool to predict ground shaking and understand how downtown Anchorage shakes, and with larger earthquakes. Say if we used, say, the Japan Tohoku earthquake as an input motion, we've been looking at that. So, and a good topic for another day, though. So let's talk about a broader response in Anchorage, and so we'll talk about how shaking changes across Anchorage a little bit more in more detail. And to do that, what we ended up doing was we took all those 95 ground motions that I'd mentioned earlier from 2004 to 2019, and we looked for essentially median values of those strong motion stations, and looked at that seismological signature, if you will, of each of the sites. And so this K212, this site is at Campbell Airstrip, and you can see that it's much lower in the spectral amplification than this K208. So K208 is at the Spenard Rec Center in kind of over by the airport. And so you can see that these signatures are different. Now, what you're really seeing here is this is the ratio or the difference, the ratio between K216, that rock site that was up on the hill up in the Chugach, and the soil site. So everything, if this site matched, if these two sites matched the rock site, you'd see just a straight line at 1, and so there would be no change here. But what we see is there are some amplifications between the soil site and the rock site, and you can see that especially here at K208, where at roughly 2.5 seconds we have a peak of about 4 times the amplification from each of those earthquakes at K208 compared to the rock site. So it really gives you a sense that how sites are stiffer or not. from an earthquake. And so one of the questions that's come up regularly is did we see, what was the 2018 earthquake like compared to just all these other little earthquakes that we have? And so one of our observations was looking at just that. And so we have these kind of funky little plots here, but what you're looking at is in the black line with the gray is kind of our average with all the other earthquakes, and then in red is the November 2018 earthquake. And when we see here at site class C, we kind of have a pretty good match, which tells us that that we didn't have much soil nonlinearity. So in the stiffer soils, we had less nonlinear response. But as we go to these softer soils, you can see that the average, the median, is much lower, and it's outside of the error bars predominantly across the softer site. And you can see it in as the sites get softer, you have more soil nonlinearity. And so what this tells us is that nonlinearity in the soil is definitely something that's important that we want to capture. With any kind of modeling and work that we do using these small earthquake ground motions, because when we have a really big earthquake, we're going to have much more nonlinearity, and so the median values of the small earthquakes just don't do a very good job telling us how that soil will behave. And so this highlights that kind of diversion between the engineer and seismologist with respect to especially softer sites and how they might behave in a larger earthquake, and why it's difficult to use those small earthquakes to predict large earthquakes. So just as a quick check to make sure that we were really seeing what we thought we were seeing, we looked at the aftershocks. And so we had a number of aftershocks of 5.7 and a few magnitude 4s, and I mean thousands of aftershocks, right? But only a few that were fairly significant. We took those aftershocks and we looked at them to make sure that we weren't actually, it wasn't just a signature from the location of the earthquake rather than the magnitude of the earthquake or the energy released. So we see here that the median values match very well with our averages from the whole database, and so we feel pretty confident that that when we're looking here, we're seeing that nonlinearity between that. So one of the other things that we were looking at is how much strain was felt at different stations. And so here in yellow we have a soft station with it's a site class DE, so it's one of the softer sites. This is Delaney Park downhole array where we've got site class D. And then if we look at CD, which is a bit stiffer soil, and then a site class C, which is even more stiff, we plot these PGAs with respect to what we call the strain proxy, which is PGV divided by the shear wave velocity at the site. We can get a sense for the different behaviors, especially as the PGA goes up, the peak ground acceleration goes up. So this is the magnitude 7.1 earthquake, and this was the Inniskin earthquake. So even though it was a magnitude 7.1, it was quite deep and far away, and so it didn't give us much strain compared to the Anchorage earthquake. So that is another tool that we can use as we're looking at nonlinear site response, and a pretty handy one. So let's talk a little bit about small earthquakes going to big ones, and we'll talk just a little bit about how do we utilize the small earthquakes to understand what the next big one looks like. And this kind of is the one of the big pieces out of my research was trying to answer this question. And so a little bit of terminology, we talked about response spectrum. It's in the time domain, so you've got period or seconds along the x-axis, and spectral acceleration in G or centimeters per second squared or what have you. And then we also have the Fourier amplitude spectrum. And so if you remember back to your days in college calculus where you're doing the Fourier transform, this is how you move to the frequency domain, where you have frequency rather than time as your domain. So you're talking about the inverse essentially of time is frequency in hertz. And so we've got two different spectra that we often work with in earthquakes, and engineers love the response spectrum. It's in the code. It's what we use. But there's a push now to actually start using the frequency domain a bit more, because there's some signatures of earthquakes that are hidden within the frequency domain that don't make it to the response spectrum. And so you're going to start seeing a lot more of that. I don't think it's going to get in the code anytime soon, but that's definitely something coming. But in order to work with engineers and seismologists, you have to be able to work back and forth between the two, and there are a few reasons for that. But talking a little bit again about this earthquake database, so we utilize all these small earthquakes to understand what that signature of each of those sites is, right, and come up with that median value of amplification from the rock to the site. And so this is something that's in publication right now, but this is our tool that we've developed to utilize the shaking from the little earthquakes to actually understand what would happen in a larger earthquake. And so from that we have an input ground motion, if you will. So this is our response spectrum for the input, or say the rock site. So the site that we'd the input motion that we put at the bottom of the model that we're talking about. And then there's something called random vibration theory, and we won't go into that in too much detail here, or any detail really, because I just want to let you know how this comes out, but we really want to look at the results and what we're seeing with the results here. So we take an input motion, we run it through random vibration, using random vibration theory to calculate a Fourier amplitude spectrum. Then we take what our site told us we had at a particular site, using those spectral amplifications. Again, that difference between, or the ratio between the rock site K216 and our site, we apply that here to this Fourier amplitude spectrum, and we get what is called the surface Fourier amplitude spectrum. And then we use RVT again to get back to the response spectrum of the site. So you don't need to. You can scratch your head a little bit about this, and we could talk in detail offline if you wanted to. But this is the mechanism essentially that we use to use those small earthquakes to understand what's going on with a big earthquake. And essentially, it's the same thing as what I talked about earlier with a 1D response analysis, where you have an input motion that you shake at the bottom of your site, and you have all of those shear wave velocities and different things for the soil deposit. Anyway, we'll get out of the weeds here and talk a little bit about how that worked. So I used that method to understand if this method actually predicts earthquake ground motions at sites using a large earthquake. And so we have the November 2018 earthquake, so this is our Delaney Park downhole array site. We have what was measured at the site here in solid black, and then using the RVT method that I just explained, what we had. And so it's interesting because what we have going on here is we have a measured spectrum. We have what was measured at the site, and then we have the dotted line is what was measured at the rock site up on the Chugach, and then using that ratio, we then compute this dotted line, and the fits are actually fairly good for most of the sites. A little bit off here The peaks are in the same spot, but we have a little bit of over prediction here. But for the most part, we have a fairly good fit when we're using this RVT spectrum. So let's go ahead and try out a trial earthquake. And our trial earthquake will be a 1964 style event below Anchorage. This is actually what the USGS models when they give us the code values for earthquakes in Anchorage and what we're supposed to design to. So this is the predominant earthquake, roughly 36 kilometers deep, and it's a magnitude 9.2. And then we have these ground motion prediction equations, the ground motion models that we can use to estimate these earthquake ground motions. So we'll go into that a little bit, but this is our trial earthquake that we'll talk about for the rest of the lecture here, and talk about what that means. Now, the NGA subduction, this is next generation attenuation subduction ground motion models. These are the models that we use in earthquake engineering to predict what the response spectrum will be at a site. And so these models are pretty important. We're not going to get into the weeds on these models. Here's a sample equation of what the ground motion model includes, and there's a whole variety of pieces to this equation to help us understand what the earthquake will be like at our site. And so with that, just to show you, over the past few years, we've had a lot of ground motion models that have been developed over time, and so interestingly enough, back in 2007 is when our model, when the Alaska model was last updated, we were sitting down here roughly 200 ground motion models that had been developed, and now we're essentially 3 times that. So the world of earthquake engineering has grown substantially since the last time that we have updated the Alaska hazard map, which then suggests to us why we should be looking at an update. And USGS is currently involved in updating the Alaska hazard map, and so we'll be seeing more on that soon. And so the ground motion models, just as we look at the November 2018 earthquake, the ground motion models, one test to see how good they are is to do this log likelihood plot and test. And so we have all of these fairly new ground motion models, and they seem to do a pretty good job of predicting what the earthquake ground motion would be like. So this is essentially using these ground motion models to compare to the 2018 earthquake and see how well they did. It's interesting that these 2 models are in our current Alaska map, and one of them you can see that it just didn't do that great a job with predicting the earthquake. And so it gives another supporting, more supporting evidence that we should be using newer ground motion models in the hazard analysis. So let's talk about that earthquake, that model earthquake, the 9.2 that we will have at some point in the future. And let's look at a few different sites and look at the response spectra. So we'll kind of talk through this just a little bit here. So the ground motion model would predict a response spectrum that looks somewhat like this. And then we have plus or minus 1 standard deviation in the dotted line. The current ASC 716 response spectrum that's in the code for site class D looks something like this. And so you can see that this ground motion model is the median value is below the response spectrum, and the response spectrum for the code, I think it's important to note, is a response spectrum for a whole variety of earthquakes, not just one earthquake, but earthquakes from crustal sources, from interslab and interface, and different distances as well. So it's important to note that this is a general response spectrum, whereas all of these other curves are specific to a single event. And so we have this one single event. We have this median value here for the NGA subduction ground motion model. And then what we have is in the blue and the red lines are using that RVT method, a prediction of what the earthquake would be like if I just ran it through that RVT model. So the blue line does not account for any non-linearity between the sites, and so you have a much higher ground acceleration than if you correct for the non-linearity. So when you correct for the non-linearity, what you actually see is that while this median value predicts a response spectrum that looks like this, we'd actually probably have higher ground motions due to that. And a number of people have asked, well, what does the 2018 earthquake look like? And was it the design event? And so here's a plot of that 2018 earthquake, and you see that it's at least for station 8040, the Delaney Park downhole array, it was not a design event. It was substantially lower than the design response spectrum. So, and even at its closest, it was still quite a ways off, and below the ground motion model predicted for that 9.2 earthquake. Let's look at a couple other sites. The stiffer site K212, that Campbell airstrip site, we can see that again we have this ground motion model prediction. We also have the ASC 716, and then we have our model, and we can see that while we have some spots that it's above, we also have some spots that it's below that median model. And when we do poke up a little bit here above this plateau that's been artificially assigned to 716 response spectrum. And then here's also the 2018 event. So this shows that this median GMM ground motion model does a pretty good job of predicting for site class C K212 site. So let's look at another one. And now this is again the Spenard Rec Center site, and we have the ground motion model. We have the response spectrum, and then we have our RVT based analysis here, corrected for nonlinear response. We're still quite above in the periods from 0.1 to 1 second. We're well above what the ground motion model would predict. And so what we can take away from that is that when we're utilizing the ground motion models, there may be some bias low based on regional information for Anchorage that should be considered in future studies. Now, as we look at other strong motion sites, if we take an averaging of those strong motion stations across Anchorage and just look at site classes, we get some plots as well. So again, we've got the site class C, CD, and D, and then DE here in yellow. And then we've plotted up this same model, and I should apologize that I've changed. We've been looking at log plots, but these are linear plots now. And site class C, we have a pretty good fit with the ground motion model and what that would predict for our large 9.2 event. But we do have some increase here above that median value. When we go to site class CD, so this portion of Anchorage, we actually see a much more significant increase, where the ground motion model would predict roughly 1.3 Gs at say 0.25 seconds or so, but this model says that it could be anywhere from 2 Gs and even a little higher when you correct for nonlinearity. So then going down to a site class D, we show that we have a bit closer fit depending on which correction for nonlinearity you have, but we have the potential where we have a large difference between what the ground motion model predicts and what our site response may be. And so I think it's important just to underscore again, this black line is based on a global set of earthquakes, what we think earthquakes would be like in Anchorage, and the red line is what we would potentially see based on measured data in Anchorage. So you get a global plot and then kind of corrected for local response. And so this tells us that that sometimes as we look at the estimates of ground motion shaking, we could end up having higher ground motion shaking than what would be predicted. So it's interesting, and we can look at site class DE as well. We see kind of the same thing, and what's probably more important here is as we see over in longer periods. So this 1 second, roughly a 10-story building, we get closer to that match, and we're pretty close. But in the softer sites, we actually see much more amplification between the ground motion model and what we potentially estimate. And so this has a much larger impact on a larger set of our building stock and the type of built environment that we have than say down here. Although we have significant shaking, it's a smaller set of building stock, whereas this one would suggest that we have greater shaking across all types of buildings. And so, yeah, again, with the VS30 estimates, you can get a sense for how the shaking with a larger earthquake may be. So with that, I think I'm getting close to complete here. So I think, I hope you've been able to bear with me, but it's important to remember the lessons that we learned from November 2018. I show you how it's a bit lower than the design response spectrum, at least at the sites that I showed you here. And so it's important that we didn't have as much damage as we could have. It was because it was a much smaller event than say a design level event. And so that's important to again take away lessons from that 2018 event and make sure that we're building appropriately. Site response analysis provides a nice estimate for soil behavior, and this new RVT based method that I presented here today really helps us utilize some of those smaller ground motions to understand what large shaking would look like. And what's really nice about that is that extends beyond Anchorage, beyond just the Anchorage strong motion network, and you could apply this to a strong motion network in Italy or some other location where they've been measuring small ground motions over a long period of time and are waiting for a larger event. This can be a tool that will help to estimate that shaking. So the median ground motion model values may be low for Anchorage. And one possible hypothesis is that these local measurements may be more sensitive to the near surface geology that we have and the variability of that compared to other regions potentially. And then there's going to be new code-based response spectra, and so the question will be, are these adequate for us as we move forward with the lessons that we are learning. And so this is again, we can utilize this research beyond Anchorage for other strong motion networks and other places across the globe as well. So a lot of neat things to consider, and I think the takeaway is that a big earthquake is going to shake shake Anchorage much more strongly than we had in the 2018 earthquake, and that our practices moving forward need to make sure that they account for that. So additional references we've got a couple publications in review right now that will be out shortly, including the one on random vibration theory and modeling with that, and then a couple others that are out now. And so with that, I ended just a couple minutes early, I think. So we can open up for some questions.
All right, great. Thanks, John. I think you did a great job there of sort of dumbing some of this complex stuff down for those of us that don't understand it very well, myself included there. So a couple of the questions. The first one is, a clarifying question, does that GMM model account for soil at all, or is that like the location at the bedrock shaking?
That's a great question. Though it accounts for soil indirectly in that you can input a VS30 value. So they've all been calibrated for different VS30 values and the impacts there. So it's kind of along that assumption that VS30 is tells you the right answer. So in the deeper soil deposits, it might not be exactly correct, but these are ground motion. These ground motion models are developed for from a large variety of earthquakes with a variety of sites, and so they do account for different soil deposits. So,
okay.
yep.
And then a theoretical question. You talked about how the nonlinear behavior of the soil will affect, I'm thinking of those plots that you showed with the sort of the 2018 earthquake, red being below the black ones. Is there a soil characterization tool besides shear wave velocity that you use to measure the amount of nonlinearity, or is it just the shear wave velocity?
So there's the nonlinearity is a function of the dynamic properties of the soil, and so in order to really understand what that behavior will be like, you take laboratory samples and run testing on that. And there's a number of there's been a lot of research in that area, and so you can account for that nonlinearity for your soil type by kind of matching with the research. And some of that research actually came from Anchorage and following the 1964 earthquake. And so there's even Bootlegger Cove type soils that have been utilized to develop those nonlinear behaviors and understanding those nonlinear behaviors.
Okay.
I don't know if that answered the question. I hope.
Yeah, it does. Basically, yes, there is.
Yeah.
there are tests, but not one in particular.
That's right.
Yeah. Okay, there's a couple other questions, but before we jump to those, I wanted to tell everybody that the password for the PDH access to PDH is earthquake. I think it's probably written somewhere as well, but just so it's on the recording. Yeah, and there's also another reminder or note that this was the repeat of the snow day, which I forgot to mention at the beginning. So just make sure you get the right password there because it's a little confusing. So, okay, John, can you see those other questions in the chat, or do you?
Well, and I was going to say, did we just kind of cover that first question? That question was, I have seen both acceleration and velocity reported at the various Anchorage sites. What are the uses of both?
I don't think you covered that.
But. Acceleration, velocity, yeah. So yeah, that's a really interesting question. acceleration is used primarily for the design of structures and that, but velocity is actually a really good indicator of damage. And so when we have peak ground velocities above a certain level, we anticipate that different types of structures will be damaged. An example is brick fireplaces, and we know that when our peak ground velocity is above a certain threshold, and we drive around neighborhoods with brick chimneys, that we'll see a lot of damage there. And so there's ground acceleration, there's ground velocity, and there's ground displacement. And we tend to look at all three, but ground acceleration tends to be the more popular method, or more popular metric that we use. So.
All right, thank you very much.
And then I think this other one was a question I had also. Is it fair to say that F sub A, the short period site coefficient in AFCE7, could be low by a factor of 2 or 3 for Anchorage?
It could be that F sub A is a bit low, and that's that's definitely something that we are looking at. The interesting piece to this is if and when we adopt the next IBC 2024, which is where some of these changes like the site class, shear wave velocity, and different site classes are going to be accounted for. They actually get away from F sub A and F sub B entirely. And there will be what they call multi-period response spectra. And multi-period, I mean, every response spectrum is multi-period, so it's kind of a silly name. And I've personally asked that they change it, but they didn't. So it's here to stay. So in ASC 722 and IBC 2024, you'll see these multi-period response spectra that are going to give you roughly 22 points along, I think 21 or 22 points along the response spectrum, and you won't have an F sub A and F sub B anymore. So there's going to be a shift there, because we'd actually looked at potentially modifying F sub A and F sub B, but because of the shift in the building code, we didn't see a lot of return on that research. So.
Great, thank you. So I'm actually going to ask one other question. We're short on time here, but on the more practical side, is there anything, so besides actually just increasing the acceleration values in the code for short period buildings, is there anything which would have the effect of essentially, if we're talking about 1 or 2 story short period buildings, especially light frame construction, we're just talking about adding more shear wall, or potentially allowing more deformations or some other more exotic thing. But besides that, is there anything geotechnically in terms of the foundations that would do anything to mitigate these, like I'm thinking of like deep helical piles or anything like that, or is the soil just too deep? The soft formations, are they just too deep to do anything?
Yeah, I mean, there's that's a great question, and really it's going to be constructing the structure to handle it, because like you say, it's pretty deep, and these earthquake signatures are going to fall beyond the depth of reasonable depth of improvement. So I think the ground motions will be what they are, and it will really just be the structure will need to be able to handle those kinds of accelerations.
Okay. Well, why don't we, there's a few other questions, but I think we'll take them offline. John, I think they're getting pretty technical, so we're short on time. So I want to thank John for this presentation and for being part of the UAA seminar series. And again, the password for the PDHs is earthquake.